The name of our idea is Motorbike Helmet with HUD navigation and fall detection system. This is Ritik Gupta.
This is Hardik Mangla.
This is Rashmi Singh.
This is Hemant Kolte.
This is Professor Pawarvi from RJ David College of Engineering and Mumbai. My team has worked well for this completion of the project. Thank you.
The main idea is that the system will provide navigation in both audio and video forms to the user on the visor directly, so that the driver does not need to take their eyes off the road or rely on any external support devices in case they need support for navigation.
This system also aims to provide immediate assistance in case of an emergency such as an accident by informing registered contacts about your current location. The system will also feature a custom design for the helmet shell, which will provide better ventilation and more comfort to the wearer.
Also, the expected cost of this project is less than Rs 5,000.
This is the implementation of our idea. For the prototype, we have taken an old helmet and fit our components inside. As you can see, there is an extra soft jaw lining placed, where inside we have placed our Raspberry Pi and other electronic components. You can also see that there is a display placed and there is a plane mirror placed at 45 degrees angle, so the inverted image of the display is shown correctly on the visor. Now, as you can see that I am able to wear this helmet without any problems, and when I put the visor down, I can see the image properly.
The hardware components we have used are a Raspberry Pi Zero, which is fit inside the helmet right now. This is the hard for project. The Raspberry Pi Zero W is a compact device with 512 megabytes of RAM and out-of-the-box Wi-Fi and Bluetooth connectivity. It is capable of running a custom open-source Linux OS named Raspbian OS. We use this device because of its compact size, weight, and that it would allow us to experiment with different ways with which we could implement our project due to full Python support and I2C device support. MPU 6050 and GY 521 accelerometer plus gyroscope combination chip. This device is our primary source of motion detection. We are using this chip to attempt to process the motion of a person riding a bike and detect when and how they have fallen. It is a low power, low cost, and high precision chip. SSG 1306 OLED display. It is the smallest OLED display which features full I2C connectivity and a display size of 128 by 64 pixels. This device is being used because of its compact size, which would enable us to fit it inside the helmet, and being an OLED display, no external backlight needs to be provided to the screen, making it more power efficient than an LCD screen of the same size. Software used: Android Studio, an Android app development IDE. It is very easy to use and features code completion alongside features like instant run and live preview of the layout. It uses open source Java language for code and XML for layouts. Python, using a Firebase library and a Luma library. Python is an open source programming language which is the most popular language for numerous applications. We use the Firebase library for communication with Firebase servers. We also use the Luma library for communication with the display. The latter required a lot of experimentation to generate the required output. Both of these libraries are open source. Firebase storage. Google's Firebase servers is a large platform offering different services like authentication, storage, and more. Companion navigation app. An app created by our team. It allows the user to communicate with the Raspberry Pi over SSH. In the demonstration, we will see how the user can easily select a destination and how they will be ready to go in almost no time. This is the demonstration of our project. This is the navigation companion app that we have made. When you launch this app, you will be greeted to a sign-in UI. This is a sign-in UI which allows you to sign in with either Google or email. We'll be using the Google account for this time. As you can see, there's a list of all the Google accounts that are existing on this device. Using any one of them with valid credentials, you can sign into the app. Then we have to enable the Wi-Fi hotspot on the device, which is set to a particular SSID and password. You can press the Go to Settings button, which will take you to the mobile hotspot settings, where you can do the same. Right now, this device does not have a SIM, so it has been connected to a network with the same credentials. Then we click Next. Here we load a map, a Google Maps activity. In this, you can use the context specific menu to fetch your location. This is our current location right now. This search bar over here is used to search for the location that you want to go to. For now, I'll be inputting a string known as Havre Splendor Road.
So it automatically suggests me the location's name on the map. This is using the Google Places API. Here on the map, we can see that two markers have been placed at the beginning and the destination point. You can see both of them to ascertain the location of those. And then when you press the begin button, we can here focus on Firebase, where all of these updates for the origin lat long and the destination lat long are sent. The origin lat long are updated very frequently because when you're moving on a bike, your location is expected to change very rapidly as well. You can see when you press the launch navigation in Google Maps button, a Google Maps app is launched on your device. Here you can see the actual route that you'll be taking. In our product, we'll also be featuring an audio system through which when you press start, all the audio instructions will be relayed directly to your helmet. Now we'll be seeing what is displayed when we press the launch navigation button, what is displayed on the helmet. We could not fit the camera inside the helmet. So here we are seeing an accurate representation of what the user will see. It is a directional arrow saying turn right, followed by a few numbers which are 55. So it says turn right in 55 meters. This number will go down rapidly as you come towards the turn, and then the maneuver and as well as the distance will change. During the implementation, we faced numerous issues. The first and most major issue was that we had to acquire an old helmet and cut it out properly to attempt to incorporate our hardware inside of it. However, the helmet was made to fit and we could not correctly incorporate all the hardware inside of it. Secondly, the display that we are using, it is not a popular device and has almost no community support. So we had to experiment with the available libraries and try to display what was the required output on it. We were successful in it, but it required a lot of time. Thirdly, the team members are from IT and mechanical backgrounds, so we had little to no electrical knowledge. We had to do a lot of research in the electronics and electrical background to make sure that we have the correct hardware and it is wired up correctly. Lastly, we had to attempt to 3D print the entire helmet, but due to the required costs and because the printing procedure would take a lot of time, we were unable to do that. The Android Places API was also deprecated a few days prior to us making the app.
Display, navigation logic, Firebase connectivity, navigation app, helmet shell design, location tracking have been completed as of now, but the fault detection, emergency response app have not been completed as of now, but expect it to be completed shortly. 6 out of 8 modules have been completed now. For the display shows the required output to the user. Pi communicates with the Firebase server and Android app to relay the correct information. Android app for navigation has been completed and tested. A custom cell design aimed at comfort and better ventilation has been completed.
Total cost of the project is now approximately rupees 5,000. Currently, the power bank costs us around 1,000 rupees. Using a custom power circuit can reduce the cost greatly. The helmet shell and custom parts, if manufactured at a large scale, would also greatly reduce the cost of the production. We feel that at large scale production, the overall cost of the product can be brought to much more economical level.
We think that our project should be selected for regional finals because currently no such products exist in the market, and based on a recent survey involving over 100 motorbike users of varying age groups and categories of use that we conducted, we have come to know that a motorbike helmet is the most used safety accessory, and also that the features that we are implementing in our project are some of the most requested additions that people want in their helmet. The prototype that we have constructed can be converted into a ready product with few changes in design and financial support. eYantra could give us the required visibility for our project to gather industry support. This project will not only ensure the safety of the rider, but will also improve the safety of everyone else on the road. This project is the need of the hour, and our project is not a luxury. Instead, it is a necessity. Transport Ministry has also shown interest recently in improving the design of motorbike helmets, and our project is a step in the right direction, which could be highlighted through this platform. Thank you.